Now for something completely different. I'm actually going to talk about wireless that collects environmental data. So kind of in our name, we're going to talk about the environment. And what we're going to look at is an information system that tries to put together the amount of water in the state, where it is, and what it's doing. So we're putting together an intelligent water infrastructure so we can have a unified source of information, not just data, but actual information. And the most important part is to inform all the stakeholders, such as managers, consumers, regulators, politicians, and it'd be nice if the politicians would argue at least with correct data. One of the forcing functions we refer to as a water-secure world, and we have what we call the 3 I's. Most straightforward is infrastructure. So that's civil infrastructure like dams, canals, things like that. However, society is not ready to spend any more tax money, and much of society isn't ready to do anything involving governmental organization. So what can we do? We can build stronger institutions in order to get our population to perhaps use water differently, more effectively, and react to changes in our water supply due to climate change. But for any of this to happen, we have to have better information and more accessible information. And notice the word is information, not data. Data is just numbers. Information has value attached to those numbers. We could use our infrastructure more efficiently with greater information, and institutions can be put together much stronger abilities to do things with information. An example of the work we're doing is a basin-wide deployment of hydrological instrumentation in the American River Basin. So, where's my pointer here? Oh, let's try this. Let's try something even better. Okay, Lake Tahoe is up at this corner. The north and south fork of the American River, and this is Folsom Dam, which controls the water coming out of the basin, and Sacramento is probably about here. And what we have by the end of the summer are 18 sensor networks to record a large variety of hydrological data. And each of these networks covers roughly a square kilometer area with approximately 10 to 15 actual sensor stations over that area. And both the location of the networks and the sensors within each network is they're set up in representative physiological reasons, or physiographic regions. So there might be similarities in slope and aspect elevation. It's a large basin, so we're covering about 4,500 square kilometers, and you'd like to be able to estimate snow and the amount of snowpack we have. The reason I'll be talking about snow is that the state of California, 65% of the water comes from the snowpack in the Sierras. So we have a long list of goals, important things, uncertainty in water supply, as it changes with our drought years, non-drought years, flexible operation of Folsom Dam. Right now, it's run very conservatively, and if we know there's more water in the snowpack, we could perhaps drop the dam pool a little bit waiting for it. Enhanced hydropower operations. We're currently working with PG&E, Southern California Edison, to be able to do real-time control of their hydro projects. Finally, forest management. We don't realize our forests are about twice as dense as they would be if people didn't muck around with them. And trees are big pumps. In our Southern Sierra site, over a meter of water goes up the trees in evapotranspiration. And a meter of water is more than half of the precipitation in that area. So the current way we connect data about snow is we have a few sites across the Sierras. Frank Gerke goes out once a month gets his picture in the newspaper. He sticks his pole in the ground, measures how deep the snow is. Below, it's his father. He's doing the same thing, same pole. These are not automated measurements, and they're non-representative because the measurements are made in very similar areas, usually meadows because it's easy to get to meadows. And if you're measuring in the same type of place, measuring more doesn't help you any. It also limits us to statistical forecasts, so we have to use simple regression based on, let's say, 50 years of previous data. With climate change, that data becomes moot. So our networks, we have an area about a square kilometer. We have 10 to 15 sensing stations, and then we have a bunch of repeater nodes. Because the idea, you can sort of see, every node has several links. So we have a full mesh. If one of the nodes goes out, all the other sensors can get their data back to the manager. The manager at 4 is a full Linux computer. It can do lots of calculations and interface with virtually any system. Currently, we use either the Inmarsat satellite system or cell phone communications. And we then have our, let's say, 10 to 18 different networks all coming into our central servers, both here and in University at Merced. So we bring in the press. So I got a nice feature here. What did I learn? Nobody gets the newspaper. I get the paper. It was late that day. I didn't see it. I was told by this by a guy near 80 years old. He gets the paper. This is a student, Carlos Arosa. He's finishing setting up one of our sensing stations at Echo Peak. It's about 9,500 foot elevation. And I'll show you in more detail the type of sensors we have. We have a snow depth sensor, temperature, humidity, solar radiation, incoming energy. And then buried, we measure soil moisture to do a balance about where the water's going in the watershed, and we measure soil temperature and matrix suction from the plant roots. And then a map of another site at Duncan Peak. The blue is the network manager, and you can see the green is sensor stations. They all look the same with this projector, but we have multiple links, and they are in different types of areas in this location. Why we can do it? Because this hardware, it's a wireless sensor node. It's manufactured by a spin-off from Citrus, owned by myself and a former student. Civil engineers, we designed and laid out the entire board, and it worked the first time without a prototype. So this board, 2-chip solution. We can use up to 40 sensors at the same time. Any analog, any digital, everything's done in the one CPU chip. It's a 32-bit microcontroller. We can do lots of calculations. Then the radio chip is built by another spin-off from Berkeley and Citrus, Dust Networks, which was founded by Chris Peaster. Our hardware is modular, so we can prepare it at an off-site location and drag it often many miles up through the woods and put the pieces together in the field. You can look at the data from our network in real time at that address, and the red spots are the different networks. If you look close, you can see at some of them a little yellow dot. Those yellow dots, if you zoom in, you'll see a yellow dot for every sensor node. And then you can also click on that little dot and you get real-time data. So this is being streamed out while we're speaking. So finally, thank you for having me here. I have to mention Roger Bales, who's the PI of our project. He's very involved at Citrus. He's started the Sierra Nevada Research Institute at UC Merced, and Martha Conklin, who's a co-PI and is also a professor of engineering at UC Merced. Thank you.